Up until now in the course, we have placed a heavy emphasis on understanding the translational motion of the systems we've studied. This has meant that for real-world objects, which can show lots of complicated motion at the same time, we have, in effect, been focusing only on the motion of the average position, the motion of the center of mass. Our application of fundamental principles has reflected this emphasis. Our use of Newton's second law has almost exclusively focused on understanding and predicting the translational motion of the system's center of mass, and much of our work with the energy principle as well. Our recent discussions of multiparticle systems have now prepared us to understand more than just translational motion of the system's center of mass. So today we'll begin to discuss ways to organize our thinking of other types of motion within the context of energy. Let's make this more concrete by having a specific example in mind. Consider a spring toy that consists of two masses, M1 and M2, connected together by a spring of negligible mass. Imagine that the entire system is moving with some speed, all the while the spring remains relaxed. If we focus only on the translational motion of the system as a whole, then, in effect, we're thinking of the motion of an object of total mass, m, which is the sum of the masses, moving at speed v, the system's center of mass speed. This system has a corresponding kinetic energy of translation of 1/2 times the total mass times the speed squared. To emphasize the connection to translation, we're going to start labeling this energy, the translational kinetic energy, with the symbol k-trans. Now let's imagine the same object still moving collectively at the same speed v, meaning the average position, the center of mass, is still moving with that same speed. However, now we're imagining that in the second case there's additional motion. The spring toy could be vibrating, or tumbling, or perhaps both at the same time. In this second case, our energy description of the average motion, the translational motion, would be identical to the first case. The kinetic energy of translation, k-trans, would still be 1/2 times the total mass times the center of mass speed squared. From this standpoint, the spring toy in both cases would be indistinguishable from an object that was truly point-like, an object that had no internal structure but had the same total mass m and moving with the same speed v. What distinguishes the two spring-like toy cases from each other is the extra happenings, the extra motion inside the system. The toy has internally a multiparticle structure that makes extra happenings possible, typically with energy changes associated with these happenings. The energies associated with these motions inside the system are commonly referred to as internal energies. Let's identify and name some specific internal energies, using our spring toy as an example. If the spring toy tumbles as it translates, we could describe this tumbling with an additional kinetic energy, a kinetic energy of rotation. Specifically, let's imagine we are translating right along with the spring toy. Then the motion that we would see would be something like this: rotation about the center of mass. We can associate with this rotation a kinetic energy we will call k-rotation. Let's emphasize here that it's motion relative to the center of mass. This is quite distinct from the overall center of mass motion, whose energy is already captured by the translational kinetic energy. In a future lecture coming up soon, we will learn how to calculate k-rotational. Imagine now that the toy vibrates as it translates. Here, if we are translating right along with the toy, then the motion would look like this: an oscillating motion about the center of mass, which we will call vibration. Our past experience with springs and masses can be used here to calculate the vibrational energies. There's a kinetic energy part due to the motion of the masses along the axis of the spring. We'll call this k-vibrational, and emphasize this as distinct from both the rotational and translational kinetic energies. There's also a potential energy part of the vibrational energy, U spring, which we will calculate as usual as 1/2 times the spring stiffness times the square of the stretch, using the usual spring constant and compression extension of the spring. Of course, in general, the spring toy could be doing all these motions at once. So the complete energy principle applied to this system would include changes in translational kinetic energy, rotational kinetic energy, and changes in vibrational energies, both kinetic and potential. There may be other changes in internal energy that we would need to include here. For example, if the spring toy was in water, where dissipation, say by drag, was significant, then the change in thermal energy of the toy, the microscopic kinetic and potential energy at the atomic level, would need to be included. Or, for example, if the masses in the spring were reacting chemically, then the change in chemical energy may need to be included here. In general, the energy changes that we need to account for when we are dealing with internal energies will depend very much on the system we're studying. We'll practice this in a number of examples that we'll discuss in future lectures.